guys, in chapter 8 we are going to start talking about hypothesis testing. So this is really kind of where we get into why we study statistics and what's the purpose of statistics. So when we're talking about hypothesis testing, what we're really talking about is trying to determine if I pull a sample and I apply a treatment to that sample, is there a difference after the treatment from the sample to the population that it was pulled? So let's kind of go through and talk about how we're going to do a hypothesis testing and what that means. So let's start off. Let's just talk about the definition for hypothesis testing. So it's a statistical method we use on sample data to evaluate a hypothesis about a population. So again, remember that when we're talking about hypothesis testing, we can't typically test an entire population. Remember, those are our parameters. So what we do is we pull a sample, we test that sample in hopes that we can generalize that back to our population. Remember that this is always about trying to figure out how something is going to affect an entire population by using a sample. So we're going to talk about just kind of the basic steps that we're going to go through as we're hypothesizing. So the first thing we're going to do is we're going to state the hypothesis about the population. We're actually going to state two hypotheses. The first one we call the null hypothesis, which is H sub 0. So this says, or we're predicting that the independent variable, the treatment, has absolutely no effect on the dependent variable or the score for the sample. So basically, your null hypothesis is that your population and your sample are identical, both after their treatment. Okay, that the treatment had no effect, so therefore your mean of your population is the same as the mean of your sample. Then the alternative hypothesis is that the independent variable, the treatment, did have an effect on your dependent variable. So now your population mean and your sample mean are two different values. They're significantly different from each other. And you'll hear that phrase quite often, significantly different. And that just means that the sample mean is far enough away from the population mean that it didn't happen by chance. Okay? So our second step is we're going to determine the critical values for rejecting the null hypothesis. One thing I need you to understand as we're going through all of these different statistical tests, we never accept the alternative hypothesis, okay? We only talk about rejecting the null, which is that the population and the sample are the same, or we talk about not rejecting the null. So those are our two options when we talk about whether or not something is significantly different. Is we always talk in respects to the null hypothesis. And again, remember, my null hypothesis is that my population and my sample after treatment, after my samples had that treatment, are still the same value. They're not different from each other. Okay? Now, when we do this, we have to talk about what we call an alpha level. So an alpha level is a level of significance. This is the probability that we use to define something being very likely different. Okay, so remember we talked about our sample distribution of sample means, and we said that any population or any sample we pull from a population will be slightly different from the population itself, because we're not going to pull a perfect sample that perfectly represents our population. So there is an acceptable amount of difference between a sample mean and the population mean. What we're trying to determine is if that difference is significant enough that it couldn't have happened randomly, that it had to be because of the treatment that we applied to the sample that caused that big of a difference, that significantly amount of difference. We can do this in one of two ways. We can talk about a two-tailed test. We can talk about a one-tailed test. And we're going to talk more about that here in just a second and talk about those critical regions and things of that nature. But we do have two different options on two-tailed versus one-tailed. And then we talk about the critical region. So the critical region is just that Z value, or values, depending on if I'm doing a two-tailed or a one-tailed test, where, again, if it goes past the Z value, most likely it wasn't a random thing, that it was extreme enough that there is showing a difference between, again, my sample and my population. So let's talk about this idea of the two-tailed versus one-tailed test. So a two-tailed test doesn't specify direction. Okay, it doesn't care if the difference is on the positive or the negative side, whether the sample mean is greater than the population mean or less than the population mean. Because of that, because you are saying I don't care which side it falls to, we actually end up dividing our alpha level in half. Okay, one of the most typical alpha levels you'll see when you're looking through research is an alpha level of 0.05, or basically 5%. So you're saying that the likelihood that you pull this sample and it is different from your population is less, 5% or less. That's what my alpha level is telling me. Now, when I do an alpha level of 5% for a two-tailed test, I actually have to divide that into two pieces. So 2.5% fall above, that's this right-hand shaded dark area, and then 2.5% fall below that area. We actually associate that with a z-score of negative 1.96 and a positive 1.96. That actually doesn't ever change. So if you're doing a z-test and they say the alpha level is 0.05 two-tailed, your critical z-scores or your critical regions will always be negative 1.96 and a positive 1.96. That actually never changes. Here in one of the other shows, we'll do a little chart where we talk about our critical regions for z's. Now, next chapter we're going to talk about the t-test, and unfortunately we don't have that in the t-test, but for the z-scores or the z-test, we actually have a list of critical regions and they don't ever change, so it's kind of a nice little thing going on there. Now, when we talk about our null hypothesis and our alternative hypothesis for a two-tailed test, what that's going to look like is my null hypothesis is going to be my population, or my mu equals my population mean. Again, there's no difference between my sample and my population. They're the same value. And remember, we're allowing some wiggle room in there because, again, a sample mean is not always going to perfectly line up with the population mean, but it should be fairly close. And if it's fairly close, it's not going to be in my critical regions. And then my alternative hypothesis is that my mu does not equal my population mean, that there is some type of difference. Notice I didn't put a direction on it. I just said it's different somehow. Whether it's greater than, less than, that's not my concern. I'm just saying it's different. Now, a one-tailed test, we specify a direction, whether it's an increase or a decrease. So now we're being very specific in what we're saying. We're saying we think that this treatment will cause my scores to decrease, or this treatment will cause my scores to increase. So now we're being very specific, and now all of my alpha level lies either to the left or the right of my population mean. So if I say that I think that my scores are going to decrease or be less, then my alpha level, in this case, let's stick with our alpha level 0.05, will all lie on the left-hand side of my graph. Notice that this would be my critical region right here. And notice my z-score down here is changed. It's not that 1.96 anymore because all of my 5% is sitting here at the bottom. So it ends up being a negative 1.645. So any z-score, when I do my calculation, that falls to the left of that score would be considered significantly different. So when we do our our null hypothesis and our alternative, our null hypothesis now is that our mean can be greater than or equal to, our mu can be greater than or equal to the population, because we don't care if it goes above, we're only talking about going below. So our alternative actually ends up being that it's less than our population mean. When you're filling these out, it is much easier to fill out the alternative hypothesis. So you're saying that your population is going to be less, so then you fill out your population as being less, and then you turn around and you do the opposite way for your null hypothesis. So since it's just less than, the opposite of less than would be greater than or equal to. And the same thing applies when we do the other side. When we say that we think that the treatment is going to cause the scores to increase. Now my z-score is over on the right-hand side. Okay, notice that my critical region is over here. Again, all of my alpha, 0.05, lies in this critical region, and now my z-score is a positive 1.645. And my alternative, or my null hypothesis and my alternative hypothesis, if I look at my alternative first, again, I'm saying that my mu is going to be greater than my population mean because I think that there's going to be an increase in my scores, which means that my null hypothesis is the exact opposite, which would be less than or equal to. Again, for these one-tailed tests, it's a lot easier if you'll do your alternative first, whether it's going to be lower or greater than, and then you do the opposite for your null hypothesis. And notice that for both of my null hypotheses, I have these lines underneath here under my inequality, which means the or equal to. So you're always going to get that or equal to for your null hypothesis. Okay, so again, once we've got our critical regions, the next thing we're going to do is we're going to obtain that random sample from the population. We're going to collect the appropriate data. We're going to perform the statistic that we need to do. We're going to provide the treatment, whatever that's going to happen. For right now, we're talking about z-scores. Later on, again, we'll talk about t-tests. That's when we don't know the standard deviation. Later on, we'll even talk about ANOVAs and all kinds of other different ways that we can test and see if things are different. Then the next thing we're going to do is we're going to compare what we found, our z-score that we found, with our critical region, and we're going to make a decision. Again, we only have two decisions to make. If our statistic falls outside of our critical region, so that means it's in the gray area, not in the dark blue, then we fail to reject our null hypothesis. But if our z-score falls inside of our critical region, then we're going to reject our null hypothesis. Again, remember, it's always about the null hypothesis, never about the alternative when we talk about making our decision. In the next video, we are going to do an example of what this looks like with an actual example, because I know sometimes talking about it in the abstract can be quite confusing. So let me know if you have any questions.